later to the dentist.
Okay, so it's a pleasure to have again Jan Hoppe, who is talking about membranes.
Yes, thank you very much. Nice to see. Some of you I know, some I met for the first time now. So actually, yeah, I'm old, and as you know and smile, I've been working on membrane theory for ages. But it is astonishing. Yeah, I'm solving the equations I wanted to solve all my life, maybe slightly exaggerated. So my dream is still to show. So membrane theory is a difficult problem, very difficult to solve nonlinear PDEs already classically, but it has very, very interesting, beautiful structure, and yeah, many aspects. I have only 1 hour, but for instance, 10 years ago also something I wrote a couple of papers. No, people didn't catch up on it, or I don't know. I found some dynamical symmetry for generally extended objects, which is related to Lorentz invariance. Very, very interesting topic. Then string theorists usually think that there is, of course, Virasoro algebra, and in higher dimensional extended objects, these things don't exist. That's wrong. There is some generalization of Virasoro. Of course, Virasoro algebra enters in many different ways, and some things you can do for strings you cannot do, unfortunately. But there is something, I call it reconstruction algebra. There is some underlying infinite dimensional algebra, which is a very interesting topic. Now, the last 2 years or so, I made a lot of progress with classical solutions and some kind of Backlund transformations also. Because the problem quantum mechanically is very difficult, matrix models, there are some conjectures about how, but it's not even known in the quantum mechanical case whether there are embedded eigenvalues in the continuum spectrum. And the ground state, one day I'm pretty sure for the 11-dimensional theory, it will be found. And then it will be some beautiful mathematical reason related to octonions or whatever, but we are not there yet. So what I can do is stare at these equations, and I start with a little history of classical solutions, and then I want to persuade or show you what I think is special about these equations and how one may be able to make progress. Now, the second part, which was announced about the Young-Mills theory, first of all, I don't think I will have time, but secondly, the 2-3 people I knew or I thought would be interested are actually, maybe you're also interested. Please ask me if I will make 1 or 2 comments about it if you are interested in. But like Jules, for instance, he's gone somewhere, and Ivan I met when thinking about these reduced Young-Mills theories, and I had a nice Skype conversation with André Boros, and he is just on his way back from vacation or so, and so several reasons why I may skip the second part. Now, the first classical solutions, we know membrane 60 years, 50, 60 years, but until 2 years ago, only 2 solutions were known. So everyone who studies the problem being, take a 2-dimensional surface, infinitely extended or compact, and tell the surface to move such that the 3 manifolds swept out in space-time has extremal volume. So solves the equations of motion following from the generalized Nambu-Goto action. And if you take this surface to be spherical symmetric, just a round sphere, give it some radius, then everyone who looked at the problem found that there is, of course, a solution because you can reduce it to an ODE, and the radius as a function of time satisfies some equation, and the solution is an elliptic function. So it reaches some maximal radius R0, and then it shrinks again. Of course, you can view these mathematically. These things are complicated either as initial or boundary value problems. So you can either prescribe the surface at initial time and some initial velocity, or you prescribe two surfaces and then you ask for some three manifold going from here to here. So it's a generalized geodesic problem. Membrane theory. Now, so that's one solution. It's a pulsating bubble. And the first one maybe who thought about this was Dirac in 1962. He wanted to explain the muon as an excited state of the electron, and he gave the bubble some electric charge, and then for many years nothing happened. Then my thesis was around 1980. There is actually one solution there, but it's very indirect. I mean, one extra solution, but quite complicated. It's not worth mentioning. And then in 93, I, by more or less by chance, found a level set description of one interesting solution, and it looks like this. So you take a set of points t, x, y, z in Minkowski space, which satisfy this equation for some given constant c, and then that is the minimal three manifold. So mathematically, membrane theory is just a theory of three manifolds in four-dimensional Minkowski space, which have zero mean curvature or extremal volume. And it's nice. It's even polynomial, and you can check that it's an explicit solution. Now, depending on the sign of the constant, it's some mixed surface. So in Minkowski space, always you have time-like or space-like or light-like minimal manifolds. And in physics terms, that means that the points on the surface move either with velocity smaller than 1 or equal to 1 or bigger than 1, where 1 is the velocity of light. And if you take the constant to be smaller 0, it's what we want from physics point of view. It's an infinitely extended surface where every point moves with velocity smaller than 1. It's a truly time-like minimal surface, minimal three manifold. Okay, then there is one. Then I started again in 2021 or something, and I thought about this one. Now you can do this in higher codimension. You can take a four manifold in 5-dimensional Minkowski space or so, and then these powers are different, but it works always t squared minus, I mean, this is just the Minkowski scalar product, and then t plus z to some power times a constant. And in this case, the constant you want to be positive. Now, this is non-compact, so it's an infinitely extended sheet, while this is, for every time t, a compact object, which is clear because for given t, this cannot be bigger than t squared. And it's actually a nice, completely smooth, round surface, which grows. So when t can be either negative or positive, when t becomes goes to plus infinity, it grows and grows and grows. And it's an example. So it has infinite energy, the solution. It's not immediate to see that. I mean, from here, it's not completely easy to see. The fact that it grows and grows and grows immediately means that it must have infinite energy. And it escapes existing theorems about finite time singularity formation. So for strings, for instance, not so well known, if you take a closed curve in the plane, there's a theorem that there is no possibility, in whatever you choose as a beginning curve and the initial conditions, you always get in finite time a singularity. And I always thought I'm the first around 95, but actually some Russians, Razumov and Konko or whatever, 3 authors were earlier. I didn't know that when I did it. Recently there is mathematical sound theorems about this, about strings by Tian and Nguyen, with all the, so there is no time-like minimal surface in R21 which has the topology of a cylinder. So there's no closed curve which somehow moves. It has to become singular in finite time. Now something similar is probably true for the membranes. So this is a counterexample. And actually for strings you can also find something like this. And it's a counterexample to the theorem. So something must be wrong, because mathematical theorems are theorems. So, what's wrong is that there is one point on the surface that grows, which moves with the velocity of light. The point t equals z equals minus t. So t is positive. This thing moves fast to the negative z direction. It grows, and there's one point which moves with the velocity of light. And that means in that 3-manifold there is a light-like line, and that is the reason how it escapes these singularity formation theorems. Now, at the beginning when I came in January to IHS, I found one more solution which is of this type, and it's a little bit more complicated. It starts out like the first one. But then minus 6c times r, so this is r squared. R is square root of x squared plus y squared times t plus z squared. And then plus 3c squared t plus z to the power 4 equals 0. Now this is not, of course you could bring this onto one side and square, and then it's still polynomial of degree 8. And again, you see you can choose positive or negative, and I will, well, later, maybe later if there's time, I come back to this solution. It's has some very interesting properties, and the physically interesting case is when C is negative, so this is positive. And then it describes a compact object at any time t, and I called it the fast sharp drop, because it's somewhat similar to this, but it has a sharp tip. So it's axially symmetric. It again has one point which moves with velocity of light, but it has, in addition, it has a sharp tip here. What is so interesting, I hope I can make some comments at the end, there are non-commutative versions of this. So, as I showed long ago, these membrane equations of motion can be related to matrix models. And when you look at these matrix equations, which correspond, you find exact solutions of the matrix equations. So this leads to the exact solution of the equation xi double dot is minus commutator xi xj. In terms of representations of SO21, infinite dimensional, there's an interesting point. Infinite dimensional matrices being non-commutative analogs of this sharp drop. Now, why infinite? Usually you have the rule of thumb. If you describe compact or surface, the interesting matrices are finite. and the n going to infinity limit is of course the interesting one. But here you get infinity right away. And it's not completely clear whether it's this point or this point. So one reason, actually I think it's this spot, the infinite. But I even forgot what I thought, which one it is. Sorry, it's infinite dimensional matrices, because unitary representations of SO21 are infinite dimensional, and I hope to come back at the end.
So you have three matrices, and
I'm
confused.
Yes.
X1 double dot X.
Yes. So there's a sum over J here, and so it's clear that if I want to describe the surface, I need three matrices: X1, X2, X3. Actually, it's a little bit more complicated, because you get these in light cone coordinates, these equations, and then you have only two matrices, and then the third one you construct the longitudinal mode zeta or x minus, and I hope I can comment on it. But geometrically, it's clear you need three matrices, but it's slightly more complicated. Okay, now what about this integrability, or what can you generally say? Why is there some hope that you can do something with these equations? So now let me start. We have the action integral d3 phi square root of g. G is a 3 by 3 matrix, and the equations are something like this. So you describe, we want to find, this is the volume of a three-manifold in Minkowski space, and I will mostly consider four-dimensional Minkowski space, slightly simpler. But you could take higher dimensional. So this is a set of D equations. Mu takes value 0, 1, D minus 1. Alpha beta takes values 0, 1, 2. So D alpha beta is D alpha x mu, D beta x mu, beta mu nu. And beta mu, I take the mostly minus metric. Okay, G is the determinant of this 3 by 3 matrix. G upper alpha beta is the inverse of G lower alpha beta. G lower alpha beta is the metric induced on the three-manifold M3 from Minkowski space.
So what's the third dimension? Because you said alpha beta take two values. And the third
Alpha beta 0, 1, 2.
3 values.
Okay, now this is some huge Laplacian, and it's known that not all of these are coupled nonlinear PDEs, not all of them are independent. And what makes it the case of codimension 1, d equals 4, simplest is that you have only, that this thing, Laplace acting on x mu, is always orthogonal to the three-manifold. So if you have codimension 1, there is only one direction. So if you solve one of these D equations, the rest of the equations is automatically solved. I mean, it's not easy to see, but it is generically like that. And you can make one of the equations simple by choosing particular coordinates. So you have diffeomorphism invariance. Your only hope is you're free to choose your parameters phi. So I choose, or one possible choice is, I choose phi 0 to be is our local time as a Lorentz observer. And I choose phi 1, phi 2 such that when I do this, my x mu becomes this. And it brings me to the picture of these minimal 3 manifolds, or these optic satisfying equations, as this Euclidean vector x, which moves in front of our eye as a Lorentz observer. So I have the 3 coordinates, x1, x2, x3. I have some surface described in normal Euclidean surface, which is time dependent. The points on the surface are described by phi 1 and phi 2, and t is our normal Lorentz time. We are sitting here and the surface moves in front of our eyes. Now, both geometrically and physically, only the motion orthogonal to the surface is relevant. If the surface moves parallel to the surface, it's just a reparametrization. So I can choose the x dot parallel orthogonal to the surface. If I do that, the metric becomes block diagonal. And the GAB is dAx times dBx. So that's the Euclidean metric on my two-dimensional surface. In these coordinates, one of the equations becomes simple, namely a conservation law. Because if x0 is t, then beta also has to be 0. When beta is 0 and the inverse of a block diagonal matrix is block diagonal, alpha also has to be 0. So I get it just an equation d by dt of, and then when you calculate that, you get square root of the Euclidean density divided by square root of 1 minus x dot squared equals 0. So the whole, and that's all you have to solve together with it. It's somewhat unusual, but it's true. So this object now transforms as a density, so I define it to be rho. And because it's time dependent, it depends only on phi 1 and phi 2. And this equation becomes, if you even write it in the more familiar form, in this form, x dot squared plus g over rho squared is 1. Rho you calculate by the initial conditions. And for the string case, this is just x prime squared. So people who know string theory, this is just x dot squared plus x prime squared is 1. And this equation is x dot times x prime is 0. These are these usual 0, 0, and then you go to oscillators and so on. Now, of course, you have the other equations. U equals I equals 1 to 3. And they look like this with this rho. But the interesting thing is that you can show that these second order equations are automatically satisfied if you satisfy this and this. You just differentiate these equations with respect to t, phi 1 and phi 2. You get many equations, and then you can show that generically, as long as the surface moves, it doesn't stop, some determinant has to be non-zero. Generically, this is implied.
It would be the same for string.
Sorry?
For string theory, it would be the same. You just
Same, yes. And for string theories, you can use this to completely solve everything. Because for string theory, you simply have x dot squared plus x prime squared is 1, and x dot times x prime is 0. And then you can write down x dot and x prime in terms of cosine and sines of functions, and then cross differentiation tells you, so you can write down the complete solution in terms of initial conditions. Now, for here, let me now go. Time is almost merciless running. And sorry, I have some problem with air conditioning, but it's getting too warm maybe also for you. Yeah, now let's go to the simplest case. So the one thing is codimension 1, and you need only to solve one equation, and then the rest follows. That's one observation. And let's now do a second simplification, namely axisymmetric membranes. So I now go to the axisymmetric case. And just as axisymmetric Einstein equations, there's work by Ernst, Geroch, Ehlers, other people, Brighton, Lohner, Maison, old work, there is some integrability in that case. And the corresponding case for these membrane theories would be axisymmetric membranes. So let me now assume that the thing looks like this, T, and then, so I take the surface axisymmetric. It's still complicated. So then I need only, I can write it like this. I have one U1 symmetry. And one of the equations here, A equals 1 and 2, is automatic. The one when I differentiate with respect to theta is automatic. So I get only two equations. And the two equations become, the lower one is r dot times r prime plus z dot z prime is 0. And the upper one, the dynamical one, is r dot squared plus z dot squared plus r squared times r prime squared plus z prime squared is 1. Now, one comment about rho. Very interesting object. You can, but here I put rho equal to 1. You can do that by further reparameterizations, in particular in the axisymmetric case. In the general case, more or less also you can put rho equals 1, because there's a theorem by Moser saying that on a compact manifold, all you know, all that is relevant about the density is the integral of the density. It's called the weight. So the only thing you cannot check, by changing your coordinates, phi1 and phi2, you can always make rho something different. The only thing you cannot change is the integral of rho. In the physical theory, that plays a role. It's some kind of constant that you need in the Poisson bracket description for Lorentz invariance and so on. But for technical, for the moment, let's just put rho equals 1. It makes it easier. And in particular, in the axisymmetric case, it's absolutely elementary to put rho equal to 1. Because originally, I would have here divided by rho squared. But rho depends only because of the axisymmetry on one variable. R and T depend on phi, and then I make simply change. Phi goes to phi tilde, such that d phi tilde by d phi is rho of phi. And then in the new coordinates, my rho will be 1, if I solve this equation. So it's elementary to, in the axisymmetric case. I mean, actually, then, if I want the phi to have a fixed range from 0 to 2 pi, I can only make it constant, not 1. But then by rescaling time and r and z, I can make it equal to 1. Okay, now, your question was, can I do the same thing for string theory? Yes, in string theory, I would have these equations without the r squared. And without the r squared, this is purely quadratic, and I can write down the solution. It's just this small factor of r squared which makes it infinitely more complicated. It's this quartic nonlinearity. Now, as this is physics, physics room, I dare to say something. Lately, I spent more time to speak in the mathematical community, and then they get very bored about this point. But I want to mention something. It's very peculiar. So what I could do is, and maybe one of you has an idea. There's a puzzle. I could use these equations to eliminate z dot and z prime. So it's quadratic in z dot and z prime. Prime is derivative with respect to phi, dot derivative with respect to t. So I could write z dot is some function f of r dot, and r prime, and z prime is something. Now, if I know the function f, z prime is simple. It's just minus r dot r prime over z dot. So z dot is f. And the function f is pretty complicated. I have to take square roots twice. So I write down a formula for f squared. And the formula is like this. Where this is p and q is r dot times r prime times r. So you solve these equations for z dot and z prime, and you can show that this, if f square, ff, which is the square root of this holds. And you have four choices, but one choice is simply z goes to minus z. That's a trivial choice. But this plus minus sign is non-trivial change. So there's a plus case and a minus case. Now, you see that f plus squared times f minus squared, a plus a square root times a minus a square root is a squared minus the square root of the square root. The p squared cancels, so you know that f plus times f minus is q. Therefore, if I take a plus here, I can write f plus as q divided by f minus, and then I get a formula like minus f minus or plus divided by r. And then I say, well, the compatibility is the prime of this must be the dot of that. I mean, this is the first derivative, this is the first derivative. And then I get an equation only for r. Now that equation looks like this, r double dot minus r squared r double prime minus r times r prime squared plus 1 over r p minus plus square root of p squared minus q squared is 0. So you get one lengthy second order equation for r instead of having this coupled set of first order equations. Now, when you derive this equation, people sometimes, no, I don't, it's when you look at it, you think, I can do it in half an hour or so. And you cannot do it in half an hour. It's very weird calculation. You don't directly get this equation. You have to first, you get something completely understandable, and then then you can show that what you get is equivalent to this statement. Now, the question is this, we are used to that everything comes from a Lagrangian. I would love to find a Lagrangian which gives this equation. I couldn't.
It's a usual kind of equation of motion.
Sorry?
It's a usual kind of equation.
Usual kind of equation. But it would help to know this. This is relatively new. I mean, these equations are ancient otherwise. But this is relatively new, and it's quite interesting when you think of the curve.
Because there is dot in the second. I mean, P and Q, they depend on R prime and R dot.
Yes. That's so. This term is a complication. It's easy to find a Lagrangian for that, but it's difficult. Okay, now the
Is conserved, is energy, if I think of this equation, is energy conserved by this equation or something like energy?
yes, but that's of course similar. If I have an Hamiltonian, I can get the Lagrangian. But it's clear what I can write down things in terms of R and Z. But you would think that it's immediate. I mean, you have something with R and Z, and then to make it simple and save time, I have not managed to find a Hamiltonian or Lagrangian which gives this equation.
And you conserve energy in terms of R.
Not only R, yes. There's some kind of reduction, but people who know about constraint theory may see immediately what to do or so. But anyway, now I deliberately did this slightly more complicated thing first, although, by the way, there's one more very interesting thing to say about this. So I call this E plus minus of R. That's my definition. So if I have R, the equation of motion is this.
I confused. You have to solve one equation for plus or one for minus, or it's a kind of.
I have to make a choice. It's only it's different. I have to say I consider it's like two classes of solutions. And it's again, you could think, well, maybe it helps that you have both. Again, I could not manage to make use of that. What I did find is if I now describe, so in my solution, I know I need to know only these two functions. Now, if I consider these as coordinates, R and Z, they are just a parameterization of part of R2. So they describe a curve, these two objects, and when I'm, phi. If I vary t, the curve moves. And it sweeps out some part of R2. And I can write down the metric of this object, this part of R2, in these coordinates. And the statement that this is 0 is related to the fact that the Gauss curvature of Euclidean R2 is 0. So this is related to the Gauss curvature of the curves described here 0. And that's one of the hopes to get a 0 curvature condition. So what I would like, I mean, I'm claiming, hoping that these equations are integrable, and one way to do it is to find a Lux pair or 0 curvature condition. And there is the most simple and most natural 0 curvature condition, namely that you have something which has vanishing Gauss curvature. This is third order in R and Z, this is second order. So there are some, I mean, if this is 0, this is true. I have not fully proved that if this is, then this is applied. Okay, that's an interesting, only 20 more minutes. So I now describe, after this detour, I now just go to light cone coordinates. We know many other examples, they sometimes simplify things. So I describe the same thing, this thing, in light cone coordinates. So t is tau plus zeta over 2, z is tau minus zeta over 2. My notation is slightly unusual. So tau is t plus z over 2, and zeta is t minus z. Usually people put square root of 2, and they call this x plus and this x minus in string theory. I now use as time, light cone time, tau, And the thing I need to know now is zeta as a function of tau, mu, and psi, where this part is the same but in different coordinates. So psi is simply theta, tau is t plus z, but z depends on t and phi. So it's a dynamical change of variables. For each solution, the change is different. And mu is determined such that the metric is diagonal. Now I have a problem. Because I'm not short enough. Okay, so in this axisymmetric case, the metric G alpha beta is 1 minus r dot squared minus z dot squared minus r prime squared minus z prime squared and minus r squared and then 0, 0, 0, 0, 0, 0. So I have a triply orthogonal coordinate system on my curved manifold M3. And it's known from 19th century that these triply orthogonal coordinate systems also have nice properties. Now, I describe the same manifold, the same membrane solution or motion in this way. Then I get a metric 2 zeta dot minus r dot squared minus r prime squared minus r squared 0, 0, 0. And my definition of mu is to have this block diagonality. These zeros. These zeros are automatic because of the axial symmetry, but these zeros, which correspond to this equation in the other gauge, is the definition of mu. Then there is a formula for how to relate metrics. And the formula is the Jacobian So, because psi is theta, there's one here in the change. This is Jacobian of the change of variables from originally t phi theta to the new variables tau, mu, psi. And dot here is derivative with respect to t again, and prime is. And then here you get the transposed. Tau dot, mu dot, tau prime, mu prime, 0, 0, 0, 0, 1. Now, the dynamical input is this equation, square root of g over 1 minus x dot squared is rho. And it's the statement, if I put rho equals 1, that this times this is this. This times this is this. This times this is this. So, r squared times r prime squared plus z prime squared is 1 minus r dot squared minus z dot squared. This times this is that. And I can use that to get information on tau and mu. So the equations I get is tau mu prime is tau dot and mu dot is r squared tau prime. I may have gotten the r squared. I never remember whether the r squared goes. I think it's right like that. Now, these are generalized hyperbolic version of Cauchy-Riemann equations. If the factor r squared was not there, these equations would imply that mu and tau satisfy the wave equation. And this is the heart of this axisymmetric case. You always have, wherever you look, you have these kind of equations. And you can transport, just like a holomorphic function, in the Cauchy-Riemann case of a holomorphic function is again holomorphic. when you go to yet a new system, it's sort of associative. So despite the nonlinearity, that's one statement, I cannot describe this better in such a short time, but it's a very important set of, and you meet these equations everywhere. So we also meet them here, namely so the second order equations, here, these ones, are R double dot is R squared R prime prime, and Z double dot is R squared Z prime prime. And here's an extra term, minus R times R prime squared plus Z prime squared. So these are the second order equation implied by these. And there is a partner to Z, V. So V prime is Z dot, and V dot is like this. Let's check. Maybe the R squared here is wrong. So if Z dot is V prime, no, it's right. So R squared Z prime is the dot of something. So here you get dot prime, and here you get prime dot. So again, there is a partner to this Z. And this plays an important role with Lorentz invariance. So when the equations are Lorentz invariant, the original ones, and you break the Lorentz invariance, of course, because of this axial symmetry, but you can still have boosts in T and Z. And this Lorentz symmetry is absolutely non-trivial. When you look at these equations, difficult. You have to make a gauge compensating transformation on phi to see that these equations have the boost symmetry. And for that, you need this function v actually. So phi transforms the partner of phi is this v. Okay, good. Now, how could this be useful? First of all, I think this is although this describes the same solution in different coordinates. While Backlund transformations, the purpose of Backlund transformations is of course to find new solutions from a given solution. But still there is a touch of Backlund to this, I come to that. And the second reason why I go through this is that I will now tell you what the equations in this gauge are. The equations in these coordinates are simpler than these. So they are Z prime is R dot R prime, and Z dot is a half R dot squared plus R squared R prime squared. So similar to that, first order equations relating to functions of two variables, but these are simpler because you get immediately the dot of this is the prime of that, and you get an equation only for R. So they imply that R double dot is R times R prime prime. So the simplest version of axionosymmetric membrane theory in 4 space-time dimensions is that equation. If you know all solutions of that equation, you know all, more or less up to topological issues, all axionosymmetric membranes. Now the problem is, several. First of all, I don't have intuition about these light cone coordinates. I mean, these, I know what r and z, little r and little z are. And the relation, of course, is little r of t and phi is big R of tau and mu. And I can translate solutions. And the way I found this solution is actually I found the solution of this. And the corresponding solution of this is R of tau and mu is plus minus square root of 2 mu over tau plus epsilon times tau squared, and epsilon is 4c or something like that. So you can check this is a solution of that. Then you solve for given r, you solve for zeta, then you use that zeta is t minus z, and then you eliminate mu, and then you find this level set version. So that's how I found the solution actually. I'm coming to this now because you asked 3 or 2, but the matrix model is in these light cone coordinates. So the relation now is that.
Just can you remind what is the matrix action just to have?
Sorry?
The action in the matrix model
Is the sum xi dot squared minus the trace of the commutator squared. And the commutator squared is the discretization of the metric G. Okay, now, but first, this integrability. I mean, maybe you ask me about this later, and then I can talk about it after the talk. But I have to come now at least to some further, not just this observation. So the Backlund transformation were invented in the 19th century. People looked for constant negative curvature, two-dimensional surfaces in R3. That was the theme, Gauss and Lobachevsky and that. And then Bianchi. Bianchi, they should be called Bianchi transformations, not Backlund. So Bianchi noticed that if you take one k equals minus 1 surface, for instance the Beltrami pseudosphere, you do one non-trivial transformation. That was his input, and you get another k equals minus 1, constant negative curvature, Gauss curvature surface in R3. And Backlund noticed that you can use some scaling, or he generalized the Bianchi transformation, and Lee, Sophus Lee, realized that Backlund is just Bianchi plus scaling. And the same now is here. So what is the analog? There is one non-trivial transformation. So what are the symmetries of these equations? It has two scaling symmetries. If R is a solution, alpha times R of alpha gamma tau and gamma mu is a solution. One of the two, it has to do with its polynomial and second derivative. So one of the scaling symmetries comes from if you have a minimum 3 manifold, 5 times it's also. So if you have a membrane solution, if you scale all variables by a number lambda, it's also a solution. And the second scaling symmetry is the Lorentz invariance. So the thing that is complicated, the boosts in that direction, which are very complicated to realize in this language, are simple in this language because it's known that the boosts in light cone coordinates are simple scalings of the parameters. So mu goes into a constant times mu, and tau goes, and so on. So you have two scaling symmetries. Now, what's the Bianchi transformation? It's a little bit complicated. Just as I told you, whenever you have these first order equations, you have a partner, a cousin. So the partner of z is v, mu and tau, and the partner of zeta also exists. So this is kappa dot over r squared, and this is kappa prime. So this equation arises in two different ways through cross differentiation, either from using the compatibility of kappa dot and kappa prime, or zeta dot and zeta prime. Now what you do is you start with one solution, R, and then you calculate zeta and kappa from these equations. Then you invert, and you write tau and mu in terms of zeta and kappa, then you write your original solution in terms of zeta and kappa. And then you ask, now this is just rewriting one equation, one solution. But now you ask, what is the equation for S? So if R satisfies such an equation, what's the dynamical equation for S in terms of these two parameters? And what you can prove is that it's the same equation. What this means is that if I manage to do these steps and know the function S, then I simply say this is R hat of tau and mu. I mean, I replace theta by tau and kappa by mu, and I get a new function. So there is a transformation. So if I have a solution R, I get a new solution, R hat. That's the analog of the Bianchi transformation. And then these scalings, just in the sine-Gordon equation, you can scale and see that you can now take alpha and gamma, non-trivial, and then you get from one solution infinitely many solutions. Yeah. Okay, there are two more things I want to do, but maybe I'm thinking of maybe even stopping early, and then I mean, there's something which, this looks good. Okay, let me say that. It looks great, or the proof that this function satisfies that is complicated, non-trivial. Unfortunately, this transformation is somewhat simple in these coordinates. It's just a reflection. So if I now calculate from R hat, zeta hat and kappa hat, and try to get a new solution from the next one, if I want to go to R double hat, I don't get something new. I get back to R.
There is no parameter in this transformation.
No. And so that's why I need the scaling. So what I need is I do the Bianchi transformation, and then I go to R hat alpha gamma, I scale, and then when I do then my non-trivial Bianchi transformation, I don't get the same thing back. So the statement is I can create infinitely many solutions from one given solution by a mixture of this transformation and these scalings. Unfortunately, I cannot do it. I have some examples. I can write these in terms of R. I can calculate zeta and kappa. They are simple polynomials. But I cannot do this explicitly because it's higher order polynomials, more than degree 5 or something. So I would love to have a concrete example to show how this works, but numerically you can do it, but not. Okay, I still owe you the answer to this, but maybe I do this later. And it's 1 hour, so I should stop. Would not go over time. Okay, thank you. Yeah. So I have to give people a chance to escape.
Okay. I have a question. This solution for R, this R
This one.
equals to uh, yes, it only depends on tau and mu over tau. Yes.
No, I mean, this depends on tau and this on mu over tau.
Yes. Yes. So have you tried to look at the equations in the variables uh, tau and nu equals to mu over tau, like change of variables?
Um, I know what you mean. So the answer is no. I will do. So what you think? But I think that this separation, my guess would be that it's unfortunately not generally separated.
Okay, yes.
But,
Yes.
but
It
it's
was-
worth trying, because if it works, it would be great.
Yes, yes.
And it's your contribution. Thank you.
Okay.
But probably it won't work. But I have many of these self-similar reductions. I first thought, I mean, you can, for instance, you can write R as tau to A times F of U times tau to the B, and then you find that this is consistent if this is true, and then you reduce the second order to first order. I first thought your question is that, but it was not.
Okay.
I see your question was maybe there is a general separation of variables.
Yes,
But
yes.
anyway, when you do this reduction, you find an ODE for F, first, second order, and then by some reason I don't understand, the second order equation can be reduced with some trickery to a first order ODE. And in principle, one can find other solutions that way. You had a question.
Yeah. So what's known about the stability of the solutions that you already have? And also a second slightly related question, what about just numerically solving these equations and seeing what kinds of things you can see?
Titina always and Ivan heavily scold me for making the life of other people complicated. So I can read email, I can write email, so I cannot do numerical calculations. However, no, I have. So there are numericals. There's work on the singularity formation with Eggers, who's an expert in Bristol. He knows everything. It's a water drop if it makes bloop, and he found the shape, whatever. Sorry?
The shape which you showed.
No, but similar, maybe. Anyway, so there are papers together with Eggers et al., where we look at these equations. So R dot is Z prime, and R prime is something times Z dot, and so on. And there is numerical work. So if you go to the homepage of Eggers, or you Google Eggers HOPPE, there are two papers. One just he and me, and then one four-author paper with former student and mine and the postdoc of his. And in the longer paper with four authors, there is numerical on these axiosymmetric membranes, and it shows how there's again some swallowtail singularity, or you start with an ellipse and something like that. Sokolov tried a little bit. So there was a visitor at IHS, Drinfeld-Sokolov reduction. I think he tried a little bit to holiday property or whatever, but it's not clear what the outcome was. And the second, sorry.
Just as stability of the
Stability,
solutions that
right.
you have there. Yeah.
I don't know. No. That's of course no, I don't know. I would love to say a little bit about this. Are you allowing me?
No, I'm thinking about the solution, but okay.
About what?
Looking at this equation.
So the relation to these matrix models is, I want to show how this SO21 comes nicely here. So the solutions are x1 is r times cosine psi, and x2 is r times sine psi. So you take this r, this particular solution. And then the classical solution is x1 and x2, and zeta you get from these equations here. And there is what I showed long ago is that you can write these membrane equations classically in these forms: xi double dot, this Poisson bracket, xi, xj, xj, sum over j, where the Poisson bracket is derivative with respect to mu and psi in these light cone coordinates.
So I'm sorry, this is a Poisson bracket, this is not...
So you have functions xi, which are functions of tau, mu, and psi, 3 variables. Dot is derivative with respect to tau, and this curly bracket means d by d mu d by d psi minus d by d psi d by d mu. And these equations are the same than those in these light cone coordinates. And the step, now you replace a la fuzzy sphere. Name was Madore, but it was invented by Goldstone and me 10 years earlier. So you replace functions by matrices, and you get these equations as an analog of that. So the answer, because you said 3 or 2. So originally, actually you get 2 matrices. So you get 2 infinite matrices, x1 and x2. And these satisfy, so square root of 2 times tau times x1 bar, and this is square root of 2 times x2 bar. So you take out a factor of square root of tau. And then these x1 and x2 bar satisfy in SO2 algebra, and which implies that x alpha with x beta and again with x beta is minus x alpha, maybe factor 2. And so the solutions of these matrix model equations come when you simply you replace the Poisson bracket by commutator, and then you get a representation of SO21. This epsilon it's a signed epsilon tensor. Epsilon 1, 2, 3 with lower indices is 1, and when you raise an index, you sometimes get a sign. And then you have to calculate zeta. And there is one more reason why I mention it is there's a big question whether you can have Lorentz invariance in the matrix model. Because the Lorentz generators involve zeta. And there's always a question whether you can classically you get zeta simply by solving these equations. But the matrix zeta is more is a complicated object. But in this example, I could show in a paper that in this called fast non-commutative drop, that the zeta exists, and it's a sign that it is Lorentz invariant. What's the noise from? It tells me to stop.
Doesn't tell you anything.
Sorry?
It doesn't tell you anything.
No. Maybe. Maybe just one remark about this. So there is the second half, which would have been about this equation minus 6-dimensional Laplace plus Q1 cross 2 squared. And you want to solve Schrödinger equation. So you have two particles in R3. And the potential is the square of the area spanned by the two vectors. And it's a simple, so the general Hamiltonian is trace p squared minus some I smaller j xj squared. So you take Hermitian or anti-Hermitian matrices xi, the potential is this, and p is conjugate, is our matrices conjugate to the xi's. And the simplest case, when I and j takes only the values 1 and 2, which corresponds to 4-dimensional membrane theory, and the gauge group is SU2, you get this Hamiltonian. So when xi, x1 and x2 are traceless anti-Hermitian 2x2 matrices, it reduces to this problem. And no one knows the ground state, and I recently had some idea of how the ground state could look like. It's an interesting problem. I think even Feynman's last paper was related to this. And I once saw, I don't remember who it was, I saw of some famous guy at that time in the 80s, an appendix to some unpublished work or so where they also discussed explicitly this problem. And it's, yeah. And I had an idea, I mean, it has SO2 cross SU3 symmetry. So the SO3 is clear because you square the vectors. And the SO2 symmetry has to, it has to do with of a rotation in the 1-2 space. And the only invariant variables, so this is one variable, 2v, and the other one, u, is a half q1 squared, u plus q2 squared. And people usually, when they study this problem, they take eigenvalues of matrices and then you get singular Hamiltonians. But what I noticed recently is if you take these as variables, you have a nice so when you integrate, you get measure 1, constant measure, because u is quadratic and v is quartic, and this is of degree 6. So what people usually write is in terms of some eigenvalues, this. So, but then you have to remove the measure and then you get singular Hamiltonian. That's what I wanted to discuss with Didina and Jules, but okay. Thank you for not stopping me immediately. Of course, I'm happy to talk about any aspect. If you find the luck, please. If anyone has an idea how to find the Lagrangian, I would be very grateful.
Kind of vacuum generating function.
Sorry?
Vacuum generating function. You know, when you have vacuum.
Vacuum generating function. What do you mean?
When you have some vacuum transformation from PQ to P, another P, another Q, and you try to find some function of the first Q, the second Q, and
yeah.
you take derivative, you find the momentum.
It's very similar. I mean, there's this work by Pohlmeier and Reggie and Lund, where which is very close to this axisymmetric membrane case. But I couldn't fully find it. I mean, the best I can do is these transformations on the metric, and I'm pretty sure that these triply orthogonal systems on manifolds have I mean the Dabu, Bianchi, Eisenhardt, they wrote books on these triply orthogonal systems in relation to integrability. And these solutions, but the generating function or full-fledged, I have not succeeded yet.
Okay, well, thank you very much.
You're a mathematician or physicist?
I try to be a physicist most of the time. Yeah.
No, because the stability is usually the mathemat. There are some work of mathematicians on that, but I think
There's smart guys too.
On va aller tout de suite.
yeah,
You're hungry?
yes and no. Are you usually going to lunch? So, because you said you're so utterly busy, you didn't even want to talk with me on Skype. I know, I don't need to eat, but if you're going anyway, are you going anyway? I can just join you or.
It's better now for me since I am so busy as.
So no, I don't need. I registered at IHS, but I told them I will be late. I don't want to break. My interest is to discuss as long as you have questions and maybe chat a little bit. I'm not in a hurry, but it's not absolutely necessary for me to eat. That's what I said. But
Good. I took a canteen card
I
from
mean,
you. We are going.
we can discuss. Sometimes eating provides discussion.
I have one question for Philippe. Just I want to show you one equation. Sorry. It takes only 2 minutes. Some years ago, there's a paper with Maxime, Joachim Arnland, and me, where we tried to solve these equations with zero here. And we get the following equation: Vn times Vn plus 1 plus Vn minus 1 plus 1 is n plus 1 times 2h bar. So we want to find objects Vn satisfying these recursion relations. The Vn is the absolute square of something, so they should be positive. We are pretty sure there is a unique positive solution of this so you choose V0 as an initial condition, and then the rest follows. And we believe that there is precisely one value of x, so that all further v's are positive numbers.
Just one.
Just one. And for given h bar. So you fix h bar, and then there's one value of x as a function of h bar. And we have found this as discrete Pernod 1, the alternative in the literature. But we couldn't find how people, there's this work by Grammaticos, it's horrible. They always have 4 pages, and then they quote as shown in this paper. Then you Google, you find that paper, and then they say as shown in that paper. And I've never found anything. It's horrible. And or confusing. Sorry, horrible is maybe too much, but it's tiring. And the question is maybe, have you seen?
It looks familiar, in fact. When we were looking at geodesic distance in planar maps,
Yes.
with Jeremy and Emmanuel Guiter,
Yes.
we came up on equations like this, where n now has the meaning of geodesic distance. So you're kind of measuring some correlation function in terms of geodesic distance. So it's not exactly the same, but very similar when you were looking at, I think, or triangulations maybe, or quadrangulations. You had some solution like that. We found some exact solutions,
Yes.
but looked like solitone solutions.
Yeah. And what, with whom, how can I find it?
Guiter and Boutier. Boutier. B-O-U.
And when? Like 10 years ago or?
No, 2000, well, yeah, I guess 2000 and something, and 4, I guess. Right.
You rewrote your recent paper was based on that?
No, it's an old result. And we have plenty of, there's not just one equation, there are many equations you can write, like higher order and stuff, and they all have this nice solitonic structure solutions.
You have here, you need V0, V minus 1. Or
Sorry?
V minus 1 is 0.
Zero, yes, yes.
Yeah, that's the usual thing, yeah. Because you don't have things with
So you plot, I'm very ignorant, you plot some V0 and then you solve and then, I don't know, it goes negative most of the time.
Yes. So if you choose too small or too big, then the fifth or the sixth, or eventually you get some negative, and you have to subtle choose. But that's the less important. What in general the growth as a function of x. So Vn as a function of x becomes a rational function. But the degree of the polynomials in the rational function grow much less than they should generate. So that's why Maxime, who put it on a computer, said it's integrable.
Yes.
And then we found some references to these discrete Parnavy, but they never described. They call this alternative discrete Parnavy one. But we would love to find a Lux pair or.
So Vn you have to think as a sort of discrete tau function, and as such, as usual, it's second derivative of the discrete tau function. And so the second derivative of the discrete tau function has always a structure like this. Maybe n plus 1, minus 2, maybe plus 2, minus 2. There's some shift of n, which accounts for discrete second derivative. So maybe some constant here, something new.
Yeah.
And so if you look for solutions in a form like this with shifts of n that realize the same thing as, see, this is like the second derivative with respect to n of log, right? You write this as exponential of log, right? And so log 1 minus xn, something like this, right? Second discrete derivative is the log of this. So it takes a form like this. And so these guys are Chebyshev polynomials, right? Because you can write them as q n minus q minus n, right? Something like this. So you can think of them as.
You mean the x?
Yeah, the whole thing, this thing here, right? The x, if you rescale things a little bit, usually lambda would be an integration constant, right? Which is fixed by initial data. And so it's really like a soliton solution, if you want.
Yeah, we did write it. That Bertrand suggested once, Einar. He was there, and I remember talking with him, and it was his suggestion to write Vn as tau as a ratio, tau times tau divided by tau and tau. We did that, but we could not prove that the taus are polynomials. I mean, we could calculate the first 10,
Yes.
and they are polynomial,
Yeah.
but we also could not prove it.
Right. So I'm not sure. That's something like this. Now.
So this is explained in your paper?
Yes. Yeah, now I'm trying to remember. It's a long time ago, so I'm not sure anymore if we have the n or not. Because the n is what would appear when you write down orthogonal polynomial solutions of matrix models, right? Usually you have equations like this.
Oh, that's another question. I mean, my feeling is that this should be rated to orthogonal polynomials.
Right. Yes.
But
the string equation usually looks like this, no? In matrix models, I think.
What's a good reference for that?
I mean, it's a pity that Sophia Falcone left because she.
Yeah. So who left?
She's just.
I don't know what
I don't know, Enar's book, probably. Enar's book has his, right? Enar. But that's more recent. I mean, there's older references as
And
well.
also Ivar Skrivan, she's coming tomorrow to Brussels.
The physics reports that we wrote with Jean Zindustin, for instance. We have all these
There's
equations.
Ça, c'est des temps moins pour le livre. Il y avait des relations de réponse, mais peut-être ou en protocole alors peut-être.
No, mais okay. So I was mixing up. Probably forget about this. This was a different problem. I hadn't realized there was an n here. But
Okay,
your n is yeah. Okay. So what do? Usually you have multiplication by an eigenvalue and derivative with respect to an eigenvalue, right? Which you write in the basis of orthogonal polynomials. So acting on Pn. So this is like nPn minus 1 dot dot dot. P are monic orthogonal polynomial, and this is just you integrate by parts, and it has to do with the action of v prime of x, right? So v being the potential. So typically the order of the equations here has to do with the degree of the potential. Okay, so maybe
V has some potential. I mean,
no, v itself is not the potential. V is the variable. Okay, so
I'm stupid. For me, xPn is Pn plus 1 plus.
okay, so the scalar product Fg is the one-dimensional version of the so maybe there's an n. Right? So this is a one-dimensional scalar product associated to the matrix integral dn and trace v of n with a hard measure on everything. Right? So you reduce the problem of computing the matrix integral to a problem in orthogonal polynomials with respect to that measure. And so you look for the monic polynomials Pn, such that Pn is delta nm. And then you need a norm because they are monic, so they don't have the right norm. And the norm is usually related to z, right? That is product actually something like this, maybe up to some factorial, which I forget, something like this. So those norms are directly related to the evaluation of the partition function, which is in itself the tau function. So now, to fix these orthogonal polynomials, what you do, instead of writing just the relation of orthogonality, you introduce these two operators, which are usually called Q and P, right? QPN. And so this starts like Pn plus 1 of x, and depending on symmetries of a potential, there's some coefficient, Rn. Coefficient is probably related to Vn. It's not directly Vn, but let's call it Rn, Vn minus 1. So that's when the potential is even, right? An even function of x. And then Pn is d by dx Pn of x, which is just n Pn minus 1 plus the product. So the n that appears here is the n that appears there. Okay, it will be on the right hand side of your equation. And now what you do is you integrate by parts, right? You write something like the fact that Pn is orthogonal to Pn minus 1 and lower, so Pn d by dx Pn has to be 0. Okay, but that's what, so maybe, yeah, I guess this way. And so this is the integral E n v, and then you put Pn of x d by dx Pn of x. Right, and then you integrate by parts, and that takes the v prime out of the exponential. Right? So you get minus n v prime of x, pn, pn, something like this. And there's another term.
Yeah, but this assumes that you have the three-term relation, and I'm not sure whether it's true in our case.
Yeah, okay. So, but you see, if you have a three-term relation like this, and a potential sufficiently nice, it will provide exactly something like this for you, right? Because what then comes out of this? You see, whenever you multiply x by Pn, you pick up an r, right? So if you have x, let's try to compute this v prime.
Because his v has nothing to do with your v for the moment.
No, but it will eventually. So try x squared, right? X squared Pn. So each time you multiply by x, you either go up or you go down and multiply by Rn, right? So x squared would be something like Rn minus 1. Right? So if you go down by 2, so the Pn minus 2 x squared Pn is Rn minus 1. So it's one of those terms. That's Vn minus 1. So you can imagine having I forgot the detail, but this is how you get these pieces of the equation. So the right hand side, this n, you get on one side of this equation, and the other you get from the exponent, the decomposition of n prime Pn on Pn. And so you get basically a polynomial of Rn's shifted possibly equals to n, just n. So it has exactly this structure. So you're right that you need to have some finite.
Yeah, and that I don't know whether it's true in
Well,
our
it's
case.
due usually. Okay, it's properties of what is it called? It's not symmetry, but maybe hermiticity of these Q operators. Right, because it means you can go up as much as you can go down and not more. So you go up by 1 because you multiply by x, but you cannot go below minus 1